So if that was an interesting movement, and I want to investigate it further, then what I do is I use the two positions that this poi and this poi ended up in to populate the next iteration of the table. So, and that's going to yield yet another table. And you go, okay, well, this is interesting. And you look here and you go, okay, well, let's see where that goes. And you go back up and you iterate a new table with this as the starting point. And what you end up with is, here, let's see if I can sort of, you have the first table populated by the first initial position. And you go, oh, well, that's interesting, you know, from here to here. So you use that to populate the next table. And then you go, well, that is interesting. And you do it again. Each one of these is starting the next, right? And I'm sure most of you figured out by now, but what you end up with is this really long list of tables. And there's this like trajectory or tunnel or snaky wormy thingy that's traveling through all of these tables where you're like, oh, that was interesting, that's interesting. And at some point, either it's going to happen or it isn't, at some point you're going to go, oh, wait a minute, look, I'm back where I started. And, oh, ta-da, you just invented a pattern. Or it's not going to happen, in which case you're just going to go, well, that was a really interesting series of movements that I just went through. I should remember that. But in any case, you're going to come up with patterns, or you're going to come up with interesting flow trajectories, or whatever you want to call them. And so this is sort of like the, I don't know, this is sort of like the punchline to quantum theory. It's like a way of representing all that there is to poi. It's completely overwhelming, of course, and if you increase the resolution at all, it gets very quickly, approaches like astronomical levels of data. So you have to be really careful. You have to find a close balance, or you have to do something creative with the way in which the data is being produced. But yeah, so that's sort of like the main idea with quantum field theory. What I consider to be like the most interesting part of this is if you were to, let's just say you had like the first table on the floor like that. There's several questions I have about it. First of all, we're just following one trajectory through at a time, but if you were to follow them all through at the same time, you'd get like, I'm not sure exactly what it would look like, but it would be something kind of like this. It would be like an exponentially growing, it'd be like, sorry. It would be like this exponentially growing table. It would get really big, really fast. Kind of like that, right? And what I want to know is what the shape, like if we were to look inside of this master table, which is only theoretically possible, I don't think we'll ever actually do it, but I want to know what's going on in here. There's things inside of it that are aesthetically pleasing to us, and I want to know what they look like and why. So, like if we go, oh, well, that's interesting, there might be ones around it that are also interesting, you know, different entries in the table. So there's going to be a group, and that's going to extrude in the third dimension into the next iteration of the table, and there's going to be more interesting things around it. And if we look at that in sort of 3 dimensions here, there's going to be these like extrusions in 3 dimensions, kind of like that, if that makes any sense, where this represents a series of patterns and flow trajectories or whatever that are interesting to people. Likewise with all these other ones. And then there's going to be regions that are completely annoying and unappealing aesthetically to everybody, or whatever. So that's sort of like somewhere where you could go with this. The other thing you can do is process the tables. You can process them for the minimum velocity or maximum velocity at which that particular movement is possible, while still having the tether or the chain of the poi remaining taut. So like if you're doing an isolated pendulum, you can only do it so quickly. If you go any faster, then the tether will start to slacken, and that represents to me the point at which that pattern becomes impossible. Or like if you're doing an anti-spin flower and you do it slower and slower and slower, or even just a static spin, if you do it too slowly, at some point gravity is going to start to overcome it, and whereas before here you were outrunning gravity, here you're letting gravity outrun you, and the head will start to fall into the circles, and that represents the point of failure, like the limit. So Drex and I typically refer to this as harmonic tolerance, which is to say it's the I'm starting to call it velocity tolerance for now, but it's basically the bracket within which this particular movement is possible. On the outside of the bracket, it starts to break down, it starts to collapse, or whatever. But on the inside of the bracket, it's possible. So an example of harmonic tolerance, the use of harmonic tolerance would be to say, like, okay, I've got poi 1 doing this, here. I've got poi 1 doing this, and poi 2 doing this, and then you realize, oh damn, in the spectrum of speed, these two movements are outside of each other's capabilities, so I can't possibly do these two moves together. This hybrid is impossible. Or you might go, oh, well, this move is interesting, and then you might go, oh, well, you know, this move is interesting, and then you go, yes, there's an intercept, there's a point where the two velocities are possible with each other, so this hybrid is possible. Yay. So where I really want to go with this, especially like this kind of thing, and this kind of thing, is to say, like, reorganize all of the moves that we know, and all the patterns, into more of like a genetic way. So it reminds me of the field of ornithology. From what I understand, bird science has changed fundamentally ever since the field of genetics exploded, because they realized that birds they thought were related were completely unrelated, and birds they thought were unrelated were totally related. They were like genetic sisters, you know. And to me, I think that a lot of moves in poi are considered to be related, but might not necessarily be. Or more likely the case is there's patterns that we think are unrelated but are actually completely related to each other. So I think that quantum field theory is going to be one of those times in poi where we're going to start realizing that things are a lot more connected than we thought they were, and other things are less connected. So that's one of my main goals, and ultimately I think this is going to help with things like spinning to music. Like I find there's a general lack of enthusiasm for actually spinning to the beat of music, and my overarching goal as a poi spinner at this point is I want poi to be like a visual form of percussion. I want to be able to drum in the air to the music or something like that. So I think that this is really going to help me do that. I don't know. Other people are going to do other things with it. We'll see. So let me see before my battery dies if there's anything else in here that might. This is an interesting page. We'll have to talk about this later, but it represents the relationship or the ratio of poi rotation to hand rotation. And that's how we populate some of the tables. What else? Harmonic tolerance graphs. These are going to become important later, especially equations like that. And I have a good drawing before I run out of time and batteries now. Let's see if there it is. Sort of like a nice drawing of how the quantum field tables iterate. Anyway, so more later. Thanks, bye.